Hello, everyone. I'm pulling up the chat right now. Hopefully, I won't have any weirdness. Let's see. All right, I'm trying to set up the sound properties. Yeah, okay, I've got that timestamp, so hopefully there's no issues. So I've got the chat up. It seems like there's something weird with the video. Here we go again. Yay! Let me know if there's anything weird going on with the stream, if there's any lagging or anything strange with that, because I seem to have sound issues once when I was in NOLA with Monty's particular stream when I had him on there. So let me make certain I'm live on Periscope. I believe I am. Yes, I am. Woohoo! So that works. Okay. Think I'm live on YouTube, so that works. So all right. Let me pull this up. All right, so I'm live there. All right, so today we are going to talk about... Okay, my lips seem to be out of sync with the sound. Okay, that's weird. I don't know how to fix this on here while it's live. That seems to be a weird issue that I get sometimes. Hello. Can I fix it somehow? Wait, no, stop, cancel. Discard the changes. Properties. Is it better now? I don't know. I'm trying to fix it. Hello, everyone. Hello. Huh. I can't seem to change it here. There's a, and I set it up to do the timestamp on the sound for the video. So sometimes it's weird like that. It seems to be better now. Okay. Okay. All right. So if it seems like the sound is a bit off, apologies in advance. Sometimes a weird thing happens with that. So let me go ahead and go live on Facebook. Okay, awesome. All right, so now we are on Facebook, we're on Periscope, and we are on YouTube. Is there more or less the same amount of energy now as there was when the universe was in the singularity? The laws of thermodynamics say the energy was the same. We can't increase it or destroy it. We just change its form. So let's go ahead and get started. All right, so today we are talking about thermodynamics. Did the sound go away? Did you guys not hear the music? That's weird. That's weird. Huh? Did the sound go away? That's the thing with live shows. Technical difficulties can and will happen, but, hey, there it is. There, it's back. Woohoo! All right, so today we're going to talk about Thermodynamics. Sound is good. Yay. All right. So here I have a perfect example of thermodynamics, what we call heat exchange. We know things go from hot to cold. Heat is given off, and heat, yay, sound is back. Heat is what we call entropy. Ah, that's weird. Okay. All right. Well, you'll get to hear the cool music at the end, I guess. All right. So today, let's first kind of discuss a bit what thermodynamics is. Thermodynamics, essentially, if you are a scientist involved in thermodynamics, or even an engineer, or anybody who works where you have transfer of energy or heat, in the form of work, and we got heat, just about everybody in some form or fashion has something to do with thermodynamics. And even if you're not actively working in thermodynamics, guess what? Your body is. So it's kind of important to understand thermodynamics, as it were. So first thing we got to do is talk about what a system is. So often people, especially on the internet, that is not a closed system. No. We have several different types of systems. So individuals, I find, often on the internet do not understand the difference between systems. So let's first start at the very basic, and then we're going to just run right into it. And we will talk about the second law and evolution, because people get that wrong too. So I kind of want to touch on the stuff that people get the most wrong about, or degrees of wrongness, as I like to say. All right, so a system can be a particular thing with a quantity of matter. And it's usually identified. We got a quantity of matter. We have boundaries of the system. So within the system, there are certain types of boundaries, and we're going to talk about those boundaries. Those boundaries can be fixed or they're movable. And with those boundaries, we have work and heat that can be involved, whether it crosses those boundaries or not. Now, the things outside of the boundaries, those are called the surroundings, all right? So we've got our system with a specific quantity of matter. Then we've got the boundaries that kind of hold that system. They can be moved or they can be fixed. And then the stuff around it is the surroundings. All right, so we have three types of systems. Now, we could go into the heavy details about adiabatic and diabatic. Adiabatic means without heat, no heat crosses. And then we have diabatic, which means heat can cross. So I won't get too heavily into that aspect, but please know that those are around, and there's terminology associated with that. There's also terminology associated with systems where you have fixed pressure. That's isobaric. You have fixed volume, isocaric. My brain leaves me. My physical chemistry is leaving me. But we also have boundaries where you can have fixed iso temperature. Oh, God, what's the word? Oh, well. Anyway, you can have fixed temperature, you can have fixed volume, and you can have fixed pressure, and those particular type of systems have names associated with those. I'm just focusing on the easy peasy. Isometric. Okay. That sounds almost right, but that's okay. All right, so an open system. Isotherm, that's it. Isotherm, that's right. That is the correct word. Thank you, Fenno. 3000. All right, so we have open system, closed system, and isolated system. An open system is matter and energy exchange. That means within the system, it can cross those boundaries. You can have matter enter into or out of. Isothermal. Thank you, ACS engineer. So you can have matter move into it or out of it. You can also have energy move into it and out of it. All right. People are an example of open systems. Closed. Matter stays on the planet, but only energy exchanges. All right. The Earth is a closed system. It's not an open system, but but what about rockets? It shoots off. Well, it's not so much. That doesn't happen on any substantial level to where everybody's shooting rockets off the planet and it goes into space. That didn't really happen. Not right now. Maybe someday. And then we have isolated. where nothing exchanges. So I have pictures at the top. An open system, for example, could be a test tube where you can add heat, you can drop stuff in it, you can take stuff out, right? Then we have a closed system where nothing can go into the test tube, but we can add heat to it, right? So we can heat that junk up. Now that top might pop off if we're not careful. You know, it gets too hot, and I'm going to talk about that in just a second. Then we have isolated, where nothing can get through that particular insulator. Nothing can get through that. Let's say it's concrete, unless you start breaking it apart. But essentially, that's an isolated system where you have a test tube inside an insulator and then a lid. We also constantly lose small amounts of gases due to solar wind. Yes. All right, so those are examples of systems. Here's the Earth. The Earth is a closed system because we don't have a whole lot of matter leaving this planet or entering into it. The amount of matter stays relatively the same, but we do have energy in the form of heat and light constantly going in and out, right? We can reflect light right back to space. That's what the polar ice caps are supposed to be doing. And since those are melting, all that heat that comes down is still, our planet's absorbing it, and we're not releasing as much back as we'd like, hence global warming. Isometric process, a thermodynamic process at constant volume. Okay, also isovolumetric. Thank you for that. All right, so Earth is a closed system, okay? Now, within this closed system, we can have open systems, right? People, living things, ecosystems are open systems. We exchange matter and energy with our surroundings. Thus, humans, animals, plants, microorganisms, and the ecosystems they reside in are all examples of open systems. All right, you eat things, so you're intaking matter. You're getting energy from these things, and you're releasing energy in the form of heat. Is matter a form of energy? Matter is not a form of energy. Matter can be shifted and changed, right? We can change matter into various forms. Now, through certain chemical reactions, we have to put energy into something to rearrange it, right? Or if we take something apart, sometimes that releases energy. That's why ATP, adenosine triphosphate, is a wonderful energy molecule for us, because those phosphates pop off and that releases energy into the system once those bonds are broken. So that's why our cells use ATP. Now, ATP in itself is an energy, but when you break those bonds, you release energy, right? That's kind of the difference. Matter can play a role in energy, but it is not in itself a form of energy. I hope that worked that out. If not, feel free to also ask me questions as we're going through. If you have any, I'm happy to answer whatever pops up. If you're on Facebook, I can't see your questions right away because unfortunately the service that I use doesn't pull the Facebook questions into there, but I can answer them later. So just please feel free to ask and I can respond in line after the video uploads. All right. I already did this one. Next slide. All right, so we're going to now kind of touch on, since we got very, very teeny tiny basics of what a system is, the boundaries and, heat, and we'll talk a bit about work. We have 4 laws of thermodynamics. A lot of people only talk about the first and second. They don't realize there's one called the Zeroth Law, and there's also a third law. But oftentimes what we see on the internet and various types of media and on the TV and stuff are people talking about the first and second law. It's kind of like everybody remembers like the first couple amendments of the Constitution, and then they don't know that there's others and that others were kind of repealed. They forget that part. They don't understand that because that's not what they're heavily exposed to. Same thing with science. There's a zeroth law and there's a third law, and we're going to talk about all of them. You always like the Dane law, huh? All right. So the zeroth law kind of talks about equilibrium. We needed this in order for us to calibrate thermometers, and I'll get into that in just a second. The first law is kind of like the conservation of matter law. Energy is conserved, its form can be converted. So we can convert energy, but we're always going to have the same amount we started or ended with, right? The second law, energies can flow and reach equilibrium. Ooh, actual science. Crazy talk. I know, it's like thinking and stuff. Boy, we have to actually use our brains this morning. I hope you all had your coffee. So energies can flow and reach what we call equilibrium, where they have the same amount. We see this in diffusion. You know, diffusion, if we look at molecules transfer across a membrane, you're going to have equal amounts at some point in time of the molecule on either side. It's equilibrium. There's a funny reason why they named it the Zeroth Law, and I'll tell you in a second, because science is weird. And then the same can be said about temperature and heat. Eventually, it's going to reach equilibrium. All right, so third law, this is the driving force for equilibration uniquely defined. Okay, so essentially, the third law talks about reaching absolute zero, which we don't think can happen anyway, but you know, it kind of rounds out the rest of them, especially in regards to entropy. So this is Zeroth Law, kids. What's this crazy stuff they're talking about? All right, so the Zeroth Law is actually quite important. You're literally about to ask why they called it the Zeroth Law. All right, I'll answer that question first. The reason why they called it the Zeroth Law is because it was established after the other laws were established. So they had already started calling the first law the first law and the second law the second law. But the Zeroth Law is, you have to understand that first, because it's quintessentially why we have, how we can calibrate thermometers. Because they had already started counting 1, 2, and 3, and they're like, wait a second, we need to talk about how it is that we can measure temperature. And so that's why they called it the Zeroth Law. The Zeroth Law came to be for that reason, because we have to understand about heat transfer and how to measure it before we can jump to the first, second, and third. So they're like, yeah, we kind of need to know that first. So, all right. Aha! So the Zeroth Law, I didn't even know there was a Zeroth Law until I took physical chemistry. How sad is that? So in undergrad, when I was taking physical chemistry, the majority of that class is primarily nothing but thermodynamics and the ideal gas law and all the derivations of it, and the Maxwell's equivalencies and things like that. And you really need Calculus 3 to get through that class, and nobody in that class took Calc 3, and that was much to the professor's dismay. So we both basically we basically focused on the theory. And then we, had to do some calculations, but we're like, dude, I never had Calc 3. I got through Calc 1, and then the rest. I would really like to take a class on thermodynamics, because it's just utterly fascinating. So back to it. Thermodynamic equilibrium and temperature. So essentially the Zeroth Law talks about two objects are separately in thermodynamic equilibrium with a third object, all right? Then they are in equilibrium with each other. So if you have object A and B are the same in heat transfer and temperature as the thermometer, because they are at equilibrium with the thermometer, all right? So if these two objects were to touch, we can see that the temperature stays the same, and this is how we can calibrate thermometers. All right, so Calc 2 is where I changed majors. I believe it. Oh, goodness. Yes. So I will talk about entropy, and I'll talk a little bit about information theory. And there's a really, really cool book that I read for physical chemistry that talks about thermodynamics in regards to biological systems, and it mentioned Maxwell's demon and things like that. So if you really want to get into some nerdy talk after this, I can link you to some really cool books. One of them is the Touchstone of Life, I believe. That was the book. It's pretty cool. All right, so that's the Zeroth Law. We need the Zeroth Law so we can calibrate our thermometers, our thermometers. Okay, so here is the first law. And we got a really cool engine going on here. It's an extension of the conservation of matter, sorry. That should say conservation of matter. So it's an extension of conservation of matter, but it's conservation of energy. So every system in equilibrium, that means the same energy and matter in a constant state, all right, has a specific amount of internal energy. Now that amount of change in internal energy, because it can change, your internal energy can increase or decrease. So that amount of change in internal energy between two particular equilibrium states is equal to how much heat was added and how much work the system put out. All right. All right. So here I've got a couple of chambers here. So we're going to dig a bit further down into this particular graphic. So here I have some chambers. Each one of these have a specific amount of internal energy. And so we can measure the change. Now the change in that internal energy that's going on in between these particular chambers, we have this dark red one, this light orange one, and this one that kind of ends up blue. And then we have this input of energy of heat here. So we have this heat that's added. That's the red here. This heat is added. And so inside this chamber, this heat is causing a certain amount of work to happen with these pistons. And it's going across the board. So the change in energy inside these chambers is going to be equal to how much heat we add minus the amount of work done. Because that work, that energy there, that's in coordination with this added heat. So we have to take that amount of work subtracted from the heat. And then that's going to be equal to how much change happens in these particular chambers. Isn't that neat? So heat goes in, the pistons move, the energy change happens in the chambers. That's going to be equal to that amount of heat that's added, and we take out that work. So, oh goodness. So, here's another example of the first law. And this is where I spent a lot of time. I took about a year's worth of physical chemistry, and all of it was all the different ways to play with the ideal gas law. Does work also relate to the gas expanding in the larger chambers? Well, if it moves the piston, then yes, that's work. So if we have here in this picture, the volume increases as the temperature T increases, all right? The pressure decreases as the volume increases. And this, the ideal gas law that we have shows this mathematical relationship of matter. That's the little n. N is the number of moles. All right, so we have N, and it shows the mathematical relationships of the number of amount of matter, the volume, the pressure, and the temperature. R is a constant. It doesn't change, all right? And there are various, there are different values of R, but those values have to do with what kind of pressure you're dealing with. Is it bars or is it atmospheres? So that value only changes if your particular units change in regards to, if you know, the type of pressure. That is a cool diagram, isn't it? Heat goes in, work goes out. Can't explain that. Oh my goodness. Are we talking about the tides? We all hate going to work. Okay. So in this case, you know, and then something to point out with the first law, it also talks about enthalpy. And I could throw the enthalpy equation up here, but sometimes people have a genuine fear of math. But just know that enthalpy includes potential and kinetic energy as well as internal energy. So what does that mean? If I were to increase the amount of molecules in this chamber, so let's say I decide to add more little black dots inside, you know, inside of our little mass meter here, all right? If I increase the amount of molecules in this chamber and the volume stayed the same, the pressure would go up, right? We're increasing the amount of stuff in a thing, that's going to increase the pressure. So this is how we can see this in this particular equation. There's mathematical relationships, all right? If the volume goes up, the pressure goes down. Now, if the if the volume decreases and the pressure goes up. So it's kind of like that. But it's also the same with the number of molecules. All right, so in this particular mathematical relationship, if I increase the temperature and I don't, let's say the molecules stay the same, if I increase the temperature, what happens? The molecules will increase in what we call kinetic energy. That's kind of part of enthalpy. They'll start moving around. This changes the enthalpy. Now, if the volume did not increase, so if we didn't allow that piston to go up with those moving molecules, then what would happen? So the pressure would increase, right? So if I start heating up all these molecules and I lock that piston in place, then the pressure is going to increase. Same volume, larger pressure would also mean higher temperature, wouldn't it? Yes, it should. Because if you're increasing the pressure and you're keeping the volume the same, then yes, you should, according to the mathematical relationships, increase the temperature. Now, if I continue to increase the temperature without allowing an increase in volume, the system could explode. So this is why we don't heat up aerosol cans. It's a really bad idea. So don't heat up aerosol cans, because things over time, if you increase the temperature, it's going to increase that kinetic energy of those molecules inside the can and cause it to go boom, right? That is essentially the first law. All of these different variables play a role. So let's go. It will explode. Yes, it will absolutely. There's like probably a whole section just on YouTube of people proving the first law just for us. And they probably get Darwin awards in the process, right? All right. So this particular diagram comes from NASA. NASA is has a really great website. They only go into the zeroth, first, and second law on their website, but they do have really good examples of if you need further explanation of the at least those three laws. Oh goodness, you have to see what happens when you throw a bottle of propane into a fire. I think they call that "Hold My Beer" on YouTube, where they're like, oh, you want to see something cool? Hold my beer. And then people are out in the woods and they're doing stupid stuff like throwing firecrackers into into like a bonfire. And I'm just like, why? That's what Mythbusters is for, so we don't have to try that at home. Yeah, and that's what the Darwin Awards is for, to teach us lessons why we shouldn't. So let's talk a bit about the second law, because there's a lot of people that get confused about the second law. Now, essentially, the second law says, it's called, hey, why? There exists a useful, and this comes from NASA, there exists a useful thermodynamic variable called entropy. Yes, entropy ain't what it used to be, right? A natural process that starts in one equilibrium A natural process that starts in one equilibrium state and ends in another will go in the direction that causes entropy of the system plus the environment to increase for an irreversible process and to remain constant for a reversible process, okay? So, normally in natural processes, you're going to have reactions, chemical reactions, that are going to move toward it causes the most chaos, right? So it's kind of like Gotham without the Batman at all. Arkham Asylum gone loose. That's what nature wants. So we've got an increased chaotic state. That's what it tends to do in irreversible processes. But it remains constant for a reversible process. There are reversible processes. So let's talk a second about an example of that. Let's see. Now this is an example of a reversible process, and it happens all the time. But the entropy stays the same. No Batman, no. Gotham is on a bender. That's what entropy favors, right? All right, so here in this case, we have a block of ice, it melts. We have an increase of disorganization, increase of entropy, right? Increase of disorganization. Now we, cool it down, it forms a block of ice again. It's an increase of organization, therefore entropy decreases, but it's the same. You will have the same amount of increase as you do decrease. It's equal. The overall entropy is zero. The net entropy is zero. It increases, decreases, and it's a cycle there. That's assuming that you have the same amount of molecules that you started out with, right? Okay, so we've gone through these two different states. White Rabbit Project. I haven't seen that. All right. Let's talk about the second law in regards to genetics. You guys want to talk about that? Because people get that wrong often. All right. So here we are. We've got DNA replication going on here. I just thought that was a pretty cool graphic, so I wanted to throw that up there. So information entropy. There's an entire division of science that's based just on information and entropy, whether it be in computer technology or in biological sciences. There are people out there that are trying to study how much entropy is released in regards to making genetic code. And so one of the things that they look at is, I believe, the Shannon equation, and the Shannon explanation of essentially information entropy. All right, so let's talk a bit about DNA. Much like water going back into an organized state, ice, putting nucleic acids together in a highly organized state known as DNA decreases entropy and increases information. Now we can have, and this is also what we call information enthalpy. So when we're going through the process of replicating DNA, all right, it's reading the code. We have our polymerase going through and it's reading the code and it's pulling in nucleic acids and it's adding more. Our helicase is unzipping that DNA, reducing that torsion, that energy that causes, because what happens if you take a rubber band and it's twisted up and you hold one in and you start pulling the other, or you can do it with your shoestrings. If you twist up your shoestrings into like a helix and you hold it tight like that and you start unraveling it here, if you don't allow some kind of release on this end, it's going to cause your DNA to snap. That's what helicase does. So you have enzymes that lower the amount of energy that's exuded that would cause damage to DNA. All right, so you have things that are kind of in place to kind of help with that. But the thing is what we have is an increase of information enthalpy. There's a whole section of science that does nothing but study how energy is used to be put into information. Now, and I had mentioned before, enthalpy is potential energy with kinetic and internal energy. Now, evolution does not violate the second law. In fact, it's an example of not only the first law, but the second law as well. Information is a form of organization. So energy is being put into forming DNA. Now, people will talk about the second law violates thermodynamics. No, it doesn't. Evolution does not violate it. A closed system, okay, we're talking about closed systems, does see an increase in entropy. Isolated systems do have a substantial increased entropy, but we don't really have a lot of isolated systems on this planet or in the natural world. We really don't see that because things can still interact with one another. You're never a totally isolated system. Now, you could be by yourself in a concrete building, okay, with nothing around, and you still have bacteria on your body. I cannot think of an example where there would be a solely isolated system that doesn't interact with other matter or energy on this planet. All right. A closed system does increase in entropy. All right. Now, what people tend to get, evolution increases the net entropy on Earth. Yes, it can. But you also have to take into consideration, and I'll talk a bit about this in just a second, about what if we're looking at one particular aspect, and I'll focus primarily on genetic mutations and what that entails. All right, so this disorder there's nothing that says that entropy has to be exclusive to DNA. you can have disorder occur elsewhere within this open system known as people. Nature generates disorder and order all of the time. So nature generates disorder and order all of the time. And we still lose most energy as heat from our body. So us just existing, we're still, even if we take in, food in the source, our source of food being primarily glucose, sugar, whatever. Even if we take that in, our body processes chemical energy, but we still release the majority of it in the form of heat. So we still contribute to entropy overall just by existing. But that doesn't mean some of it can't be used for informational purpose in the form of genetics. All right, so let me talk a bit. You're not going to read all that, so I'm not going to make you. That is mostly for me. So, and I wrote that this morning. Hallelujah. So, mutations in DNA. So, if we are looking at mutations in DNA, they do generate disorder. All right. So, if we're looking at a single point mutation within the genetic code, that generates disorder. Now, let's say that affects an amino acid, and that particular amino acid happens to affect the making of a particular protein. That particular genetic mutation would only make a substantial impact if we were all closed systems without any exchange of matter. All right, we still have exchange of matter. We still have things that interact with us, even on the genetic level. Viruses, for one. So this is not the case. Organisms with bad traits tend to not have as many offspring, and over time, to cause a particular trait to stick in the population. So if you have a bad trait that hops up, right, and we'll even say it's a dominant trait, the likelihood of that particular trait sticking around to where it would affect the majority of a population would be exceedingly low, possibly impossible. So that particular chaos, that wouldn't necessarily stick around, and evolution would kind of kill it off. So organisms with bad traits tend to not have as many offspring, and over time, to cause a particular trait to stick around in the population. Now, if the gene pool stayed the same without any movement of new populations, we would then see an increase in these ill traits. This is also why we don't have children with family members. That would be a relatively genetically closed system if all you did was have babies with people who likely have mutations in various potential problematic code to cause it to be more pronounced in your closed genetic system. Evolution would eventually cause such organisms to die out and quickly, thus increasing this disorganization and death. The scenario is also making the assumption that no symbiotic relationships would occur. For example, beneficial bacteria. Perhaps there's a trait where you lose the ability to digest certain things. It could be that certain types of beneficial bacteria would then evolve and could live within your gut and help you break stuff down. We do have bacteria that does that. Also, you could have viruses interact with our DNA, which could in turn cause changes, possibly beneficial. We have a lot of viral DNA in our bodies now. So evolution does not violate the second law. It follows it to the letter. Yes, this is why we are probably going to see the cheetah go extinct. Now, when I worked on the Tree of Life project with Dr. McKenna, we reared ladybugs. We wanted to map the genome of one particular species, one line of ladybugs. And the problem we were running into is that since there was so much inbreeding, because we were constantly trying to make babies to where we could use them to extract their DNA and look for specific genes, because that's what they do to see how many particular genes are related to other beetles, and then that's one determining factor of how they go on the Tree of Life. A lot of the babies were dying out because there were so many problematic genes that were coming to light with this particular species. So that increases disorder and chaos. I mean, then those die out, they fall to pieces, so you have disorganization. So evolution does not violate the second law. It follows it to the letter. So people who say it doesn't, they don't understand certain aspects of evolution. Bacteria, wouldn't it be the other way around? Those bacteria able to break up the stuff we no longer digest would prosper due to the rich food sources and those with the fitting bacteria in their guts. Maybe. It may be. I mean, this is a scenario where we're trying to make it completely isolated where nothing else interacts with the people. But even then, as I mentioned before, you'll never fully have an isolated system. So even if you have people dying out because of bad traits, they eventually are going to increase the amount of entropy in the system just because their compounds are going to break down and be released as the form of heat and energy. I mean, this is a problem that we're having right now with global warming, and now we're releasing a lot of methane into the atmosphere from ice, different types of permafrost that are being released. Okay, so they would have an advantage as the bacteria would take care of the less available nutrients in their intestines by doing the breaking up. I don't know, but this is something we can think about. They've made bacteria that can eat plastic. Isn't that cool? Or nylon. Okay. Oil too. That's kind of neat. Now we're going to talk about, so I wanted to take a moment to talk a bit about the second law. And people were like, the second law. So now we're going to talk about the third law. Let me fix. Whoops. Wrong way. Here we go. The third law. All right. Woohoo. The entropy of a pure crystalline substance at absolute zero is zero. So the reason they have the third law, most thermodynamics calculations use primarily entropy differences. Okay, so that's what they look at. So the 0 point of entropy scale isn't really considered that important. The third law is discussed primarily, and they generated it primarily for purposes of completeness, because it describes where zero entropy can occur. So in this particular scenario, we have a group of atoms that are just purely this particular substance, nothing else there. It's in solid form and it's at absolute zero. All right, so what exactly does that mean, and why do people care about absolute zero? Part of that is because they kind of want to, since we've talked so much about entropy, and that's what scientists do, they're like, entropy, 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 and you're like, okay, that's not what I wanted to do. Okay, here we are. So the third law pretty much states when absolute zero is reached, how that affects atoms, pressure, volume, and entropy. So essentially, when we have absolute zero, nothing is moving, nothing is vibrating, pressure is constant, as is volume, energy doesn't change, work doesn't happen. Essentially, nothing is happening, therefore entropy is zero. So we're kind of looking at, okay, isn't reaching absolute zero like reaching the speed of light? Yeah, probably. It's just you're never really going to get there. Because the idea is we have so many, when you're looking at all the atoms, they're always constantly moving. Even when they're frozen, they still have their own vibrational frequencies. And that's something that's measured. I read scientists were able to record temperatures colder than absolute zero. They call it negative temperature. How is that possible? I haven't heard that, so you'll have to send me that link. Colder than absolute zero. Speed of light limit has to do with mass. Absolute zero just means no molecular motion, but due to quantum physics, we actually need to put energy in to get 0 Kelvin. Goodness. I haven't done a lot of work in regards to getting things to 0 Kelvin. And for all intents and purposes, since we don't have a lot of this occurring naturally on the planet, it's not considered inherently important. Because 0 Kelvin means just literally nothing is happening. And so, when would that be beneficial to have nothing happen? And so even if we were talking about if we got a person completely frozen at 0 Kelvin, if we were trying to say, okay, what about cryogenics? Well, if we got something at 0 Kelvin, completely froze a person in that state, I don't know what that would happen what would that do to a person if you eventually started to raise their temperature from 0 Kelvin to higher? That's something to think about. How would, would that, you're increasing the disorder again, but would that affect how the molecules are formed in the crystalline structure? So it's weird. Live science? Okay. It is technically colder because the entropy in the limited system is manipulated after it's brought to near absolute zero. Okay, well, thanks for explaining that, Nether. So essentially, absolute zero is just kind of used to round out all the things in regards to thermodynamics. And of course, people always want to try to reach it because it's a pretty cool thing to do if they're able to. So essentially, that kind of brings us, that's all I really have on thermodynamics. This hasn't been this has still been about 45 minute talk, so that's not too bad. So essentially, what is thermodynamics? It's the studies of the effects on a system, work, heat, and energy. And then we talked about the different laws and why it's called the Zeroth Law. And that's because they figured that out after they had already written the other laws. Like this one kind of supersedes the others and is pretty important. So we need to know that. So we have that. I do have sources, and you can never read them on here, but I do post them on my website. And so I've got all of these links. And I know you can't really read that, but I do post it on my website, scientistmel.com. How much energy did you lose on your trip, Mel? You mean my trip to New Orleans? How much energy did I lose? Gosh, I don't know. Goodness. So I don't know how much energy I lost. So I wanted to take a moment to thank my patrons really quickly, and then we can talk a bit more nerdy afterwards. Tony, James, Lauren, Jen, Carl, Melanie, Patrick, Daniel, Paula, Tim, Carrie, Cersei, Keith, Zachary, Tony, Graham, Tristan, Jennifer, Corey, and now Heavy. Thank you so much for contributing to my Patreon. They help me keep the lights on, and I'm able to get a lot of cool stuff in regards to upping my quality here. I'm going to start in a green screen soon, and they help me get my website put together, all of that, which is awesome. I probably gained energy in New Orleans. I probably did. But you can find me everywhere. I'm also on Google Plus as Scientist Mel. So scientistmel.com, patreon.com, Periscope, YouTube, Facebook, all Scientist Mel. If you like what I do, buy me a coffee once a month. I am going to start an Amazon wish list for gear to help me out with my stuff and hopefully make me mobile to where I can go to different places and stream from there. I hope to have Spirited Science going pretty soon. I'm getting the intros completed, and I'm writing the shows for that, and I'm getting together people to be on my show. So if you are a science enthusiast, you don't have to be a scientist, you don't have to have super awesome degrees in science in order to be on the show Spirited Science. The whole purpose of that is to get people engaged in science. We all sit around, we have a discussion about a particular scientist or a topic associated with science while having the same beverage, same themed adult beverage. So that's something you're interested in, message me. Find me on social media. I'm on Twitter, Google+, all of those things. And this has been the science of thermodynamics. Thermodynamic. When there's no more coffee left in it, sadness arrives. Yes, and this time right here, I've had my coffee, and I bet it's cold now. It's cold. Thermodynamics, guys, it works. Guess what? The heat is released out of my coffee, and it makes your ice cream melt, which is really sad. So let's see. Taking a trip is a closed system. You regain as much from the recreation as you lose. I'm going back through and see if I can find any other questions. Quantum gas can go below absolute zero. See, I haven't read a whole lot, and and that's something that I get to learn when I do stuff like this in regard to absolute zero with Kelvin and atoms. There are some interesting quantum effects at or near absolute zero. I've seen a few videos about it. You don't have links. Well, yeah, you have to send me stuff, because I like to learn things too. And and if I don't know something, I find people who do. Would you talk about statistical thermodynamics anytime soon? I can add that to my list. I've started doing the polls again, because I was going back through and redoing the more popular episodes in this newer format. But now I'm going back and adding, the list of polls. And I have polls on Facebook. I also have polls on Twitter. And I also put polls up on Google Plus, on my Google Plus page, as well as in various forums. And I always take suggestions. And what I do is I take whatever the total number of each votes are together. And that's what I talk about every Saturday. A close second was lightning. So lightning was a very close second this week. So I'll put lightning back in the next poll, and then I can toss in statistical thermodynamics. But this has been a lot of fun, guys. I hope you learned something. Some people may not learn some things, but it's always kind of fun to go back through. And it's nice to have engaging conversations about such things. If you want to know more about the math, something that I can do, let me pull that up really quickly, and I'll find, there's a really, really, really great book. Let me find it. And it talks about thermodynamics. Is it? All right, let me pull it over here. Come on. Is this it? Yep, by Lowenstein. So I'm going to put this up on my big screen here, and so you can see. So this particular book by Werner R. Lowenstein. Let's see, Maxwell's Demon. So it talks about a lot of the Maxwell equations, and you might be able to find information. Sometimes the math gets a bit heavy, but it goes through the history of thermodynamics. It talks a lot about Boltzmann's entropy, how he determined it, and the information entropy trade-off. So I mentioned a bit about information theory. So something that's kind of important, especially if you want to get into the biological aspects of how information and entropy trade-off, that particular aspect of, genetic code and DNA. This is a great book. I read it for physical chemistry, and I highly recommend it. So if you haven't checked it out, let me see if I can find what the book cover looks like for you. Here we go. I have it on Goodreads. I'll go back to this one so you can have a look. This is what it looks like. It's the Molecular Information, Cell Communication, and the Foundations of Life. This is an excellent, excellent book that goes through all of the aspects of thermodynamics in regards to molecular information, how cells talk to each other. It might be I would say it's probably an intermediate level reading, but if there's things that you don't understand, it's a pretty simple read for the most part. You should be able to skip over some of the mathematics if you find it taxing, and just kind of stick to the actual text. And you know what? And if you have questions about this book, man, just hit me up. I thoroughly enjoyed reading it. Shannon's information theory. I did touch on a little bit of Shannon's information theory, and some scientists use that particular theory in regards to trying to determine entropy in regards, and how to measure it in regard to DNA and the formation of DNA. So you can check that out as well. I think it's spelled Zeroth. I don't know if there's an E in there. See, I've looked and I've seen both, so you can check out and kind of see which one. Dawn is not a programmer. Zeroth is a word. Yes, zeroth is a word, and it's fun, and it's funny why it's called that. It's called that because they made the other laws first. But the Zeroth law is super important because the others don't make sense unless you know how to measure temperature. And so the Zeroth Law allows us to be able to calibrate thermometers. Yeah. What are the laws of thermodynamics? I just went through them, so you'll have to go back and watch again. I am a programmer. Well, if you guys have any questions at all, you know how to find me. I'm everywhere on the internet. So I'll pop this back up again so you can kind of see centered. And if you're curious, you can find me anywhere here. You write for an open source game. That's cool. So if you have questions, find me. I'm everywhere. Go check out my other videos. I'm also on YouTube. I am going to start re-recording really soon all of these different episodes that I have, but without the back and forth or the engagement. So they'll be shrunken down versions, and they'll be called Scientist Smell Shorts. It'll be all the same content, but much smaller packages in case you don't want to watch the entire broadcast of me interacting with others. So that should be available soon. I'm going to start recording those tomorrow. And so check it out. It's spelled both ways, Zeroth, with and without the E. Oh, goodness. So the Zeroth element. The dictionaries all use Zeroth, and Zeroth is only used by civilians. It's so confusing. Well, I'm so glad you guys popped on here, and I'm glad I got to see you guys. I'm glad you guys are doing well, and I hope you've enjoyed this particular episode of the Science of Thermodynamics. Woohoo! Hope you guys had fun, and you know what? I'm all over social media. Come follow me on there, and I'm going to make a new playlist for my cognitive bias series. Those little 1-minute videos I've been peppering along on all over my channel and stuff. So hope you guys are enjoying those, and if you want me to talk about a particular topic, message me, email me, go to my website. You can email me there. You can also hit me up on Twitter, Google+, Facebook. You had fun. Yay, I'm so glad. And I'm glad you're enjoying yourself. So shoot me any kind of topic ideas you want to have. I'm glad you like the stream. So didn't yet know isolated ones. Yeah, I'm so glad you guys learned that today. That makes me smile. It makes what I do worthwhile. And I hope you guys have a super awesome Saturday. And be sure to hop over to SciStrike tomorrow. I will be on that show talking about climate change. Woohoo! So have a fantastic day. Bye!